Hey everyone, and welcome. Today we're going to talk about one of the absolute cornerstones of machine learning, linear regression. It's this incredibly powerful yet surprisingly simple idea that teaches a machine how to find hidden straight-line patterns in data, turning a bunch of scattered dots into really confident predictions. But to really get it, let's start with a story. Picture this. It's 1801. An astronomer discovers a new object in the sky, calls it Ceres, tracks it for a bit, and then it disappears behind the sun. It's gone. And all the top scientists in Europe are scrambling, trying to figure out where it's going to show up again. But then this one guy, the legendary mathematician Carl Friedrich Gauss, takes a look at the very limited data they have, does some calculations, and makes a prediction that is completely different from everyone else's. And guess what? Months later, Ceres reappears exactly where Gauss said it would be. So what was his secret sauce? Well, it was an early version of the very same method we're talking about today, linear regression. This same fundamental idea that found a lost asteroid over 200 years ago is now helping us do things like predict the price of a house just by knowing its size, or forecast a company's sales based on its ad budget. It's a truly timeless and powerful concept. So how does this whole thing actually work? Well, we're going to break it down into a simple three-part quest. First, we have to find the line. What is this prediction line we're even trying to draw? Then we need to grade the guess. How do we know if our line is any good? And finally, we'll start the search. How does a machine automatically find the best possible line out of all the options? All right, part one of our quest, finding the line. The whole goal here is to draw a single straight line that best captures the relationship in our data. Now, if we're predicting something like a house price using just one feature, say its square footage, we call that simple linear regression. But real life is usually more complicated, right? So if we use multiple features, like square footage, number of bedrooms, and the neighborhood, that's called multiple linear regression. But don't worry, the core idea is exactly the same for both. We're hunting for the best line. In the world of machine learning, we've got a slightly fancy name for this predictive line. We call it our hypothesis function. But don't let the name scare you. It's literally the same equation you probably learned back in high school, y equals mx plus c. You'll often see it written like this, h of x equals beta 0 plus beta 1x. Here, beta 1 is just our slope, telling us how steep the line is, and beta 0 is the intercept, which is our starting point. These two numbers are the only things our machine needs to learn to create the entire model. Let's really dig into what those two things mean. The intercept, or beta 0, is just our baseline. It's the predicted value if our input was 0. But the slope, beta 1, that's where the action is. The slope tells us, for every 1 unit increase in our input, how much we expect our output to change. So in our house price example, the slope tells you exactly how much the price is predicted to go up for every additional square foot of space. It's the real engine of our prediction. Okay, so we can draw a line. In fact, we could draw a bazillion different lines through our data points. So the big question is, how do we know which one is the best one? How can we actually score them? This brings us to the second part of our quest, measuring the error. For every single data point we have, each individual house in our data set, we can measure how wrong our line is. This little error is called the residual. It's just the vertical distance between what our line predicted the price would be and what the house actually sold for. A tiny residual means we made a great guess for that house. A huge residual means our guess was way off. Now, we need one overall score for the entire line, not just for one point. And for that, we use a metric called mean squared error, or MSE. It sounds a little mathy, but it's really just 3 simple steps. First, we find all those little errors, all the residuals. Step 2, we square each one of them. Now, this is a clever trick. It does 2 things. It gets rid of any negative numbers, and, more importantly, it punishes the big errors way more than the small ones. Being off by a little isn't so bad, but being off by a lot is a huge problem. Finally, we just take the average of all those squared numbers. And that right there, that is our one and only goal. The best possible line, the one we've been searching for, is simply the line that makes this mean squared error score as tiny as it can possibly be. Okay, so we have our mission. Get that MSE score down to rock bottom. But how does a computer actually do that? I mean, it can't just try out every single possible line in the universe, right? That would literally take forever. This is where the real machine learning magic happens, in the final part of our quest, the search. I want you to imagine a giant 3D valley. Seriously, picture it. Every single spot on the ground of this valley represents one possible line, one specific combination of a slope and an intercept. And the height of the valley at that spot, that's its error score, its MSE. So a high peak in the landscape means a terrible line, while a low point down in the valley means a really, really good line. Our mission is to find the absolute lowest point in that entire valley. So how do we find that low point? We use a beautiful algorithm called gradient descent. Think of it like this. You're standing somewhere in that valley blindfolded. To get to the bottom, you'd feel the ground with your feet to see which way is the steepest way down, right? And then you'd take a step in that direction. That's exactly what gradient descent does. It starts with a random line, calculates the gradient, which is just the direction of steepest slope, and takes a little step downhill. And then it just repeats that process over and over again, taking one step at a time until it settles nicely at the bottom. Now, how big are those steps we're taking down the hill? That's a super important setting called the learning rate, and it's a trade-off. If you take teeny tiny, cautious baby steps, you'll definitely get to the bottom, but man, it might take a really long time. On the other hand, if you take these giant, huge leaps, you might get there faster, or you could completely overshoot the bottom and just bounce around from one side of the valley to the other, never actually finding it. Getting that step size just right is a huge part of the art of training these models. Okay, deep breath. We figured out how to find a line, how to grade it, and how to search for the best one. Now let's zoom out and talk about what this all looks like in the real world, both its incredible power and some of the things you have to watch out for. So, once you've done all this work and found your best line, you need a simple way to tell someone how good it is. That's where a score called R-squared comes in. You can just think of it as a report card for your model. It's a grade from 0 to 1. An R-squared of 0 means your model is basically useless. An R-squared of 1 means your model is a perfect crystal ball. So let's say you build a model and you get an R-squared of 0.80. What does that actually mean? It means that your model, just by looking at one variable like square footage, can explain 80% of the reason why house prices are what they are in your data. The other 20%? Well, that's just stuff your model doesn't know about. The neighborhood, the age of the house, if it has a nice backyard. It's a fantastic at-a-glance way to see how much of the story your model is actually capturing. And believe me, this tool is a total workhorse. It's used everywhere, predicting house prices, of course, forecasting a company's sales based on their marketing budget. Farmers use it to estimate how much their crops will yield based on rainfall. It's even used all over finance to assess risk. It's almost always the first model you reach for when you have a prediction problem. But, and this is a big but, it is not a magic wand. Its biggest weakness is right there in the name, linear regression. It fundamentally assumes that the relationship you're modeling is a straight line. And while life isn't always a straight line, is it? It's also really sensitive to outliers. Imagine you have a data set of normal houses and then one billionaire's mega mansion. That single extreme data point can yank the entire prediction line towards it, making it less accurate for everybody else. So after all this talk of valleys and residuals and report cards, if you just remember one thing, let it be this. This quote from Geeks for Geeks absolutely nails it. The goal is to find a straight line that minimizes the error between the observed data points and the predicted values. That's it. That is the whole game in a single sentence. So, linear regression is incredible. It gives us this powerful way to draw a simple, straight line through all the chaos of the real world and find a meaningful pattern. It's an absolutely essential first step in teaching a machine to see the future. But it also leaves us with this really fascinating question. What do you do when the real story isn't a straight line? What happens when the truth is curvy? Well, that's where the journey into machine learning gets even more interesting. Thanks for joining me.